Okay, here we have Energy Math video number 2, where I'm going to work through all the problems on the whiteboard and show you how to get all the right answers here. So I am toggling back and forth between your Energy Math assessment on Schoology. You can't see that, unfortunately. My setup here is not quite as fancy as what I had during COVID, so we're gonna try this and make it work. So it says to watch Energy Math video number 1 first. Hopefully you've seen that. Write out the work for the problem on a fresh page in your notebook, labeled Energy Math. Round all the answers to the nearest whole number for the quiz. It's going to ask you to put your answers in a text box. And if it's not rounded correctly to the nearest whole number, it's going to mark it wrong. Don't put any commas in for the numbers, like 5,231 doesn't need a comma, like 5,231, just 5,231. So let's go ahead and go through the questions. And we got 12 questions here. Let's see how it goes. Okay. So the first question, we have an environmental science teacher planning a trip around Europe. I wonder who that could be. One of the legs of the trip will take her from the tidal island of Mont Saint-Michel to the historic caves of Les Aziz. Both places are UNESCO World Heritage Sites in France, and they are a 618-kilometer drive apart by car. There's no direct train service between the cities, but she could take trains from 4 different cities, between 4 different cities, to eventually arrive at her destination in 13 hours and 40 minutes, over 929 kilometers. This would cost $147 a person. If she rented a car, it would cost $33 a day for the rental, plus the cost of fuel. And she would arrive in 7 hours, over 618 kilometers. So that is a lot of information. Plus you have a data table at the top with even more information. And the question is, how much energy in megajoules, capital M is mega, would be used for each mode of travel for just the teacher? So we want to know how many megajoules for the train. And the only place megajoules is mentioned is in the data table at the top. So hopefully you're on Schoology in the assessment looking at question 1 and you see that data table here with me. And so we're going to do for the train and for the car. So for the train, it says 1.1 and it's megajoules per kilometer per passenger, if assuming the train is full. We're going to assume the train is full. And then for the car, it says it's 3.6 megajoules per kilometer per vehicle. So for the train, we're going to say, okay, 1.1 megajoules per kilometer per passenger. So we got 1 passenger, just the teacher. And the kilometers that we're going to go through for the train ride, if you reread that question, you should see that it's going to be 929 kilometers for the train ride. And we're going to convert this into megajoules. And so we've got kilometers down here, megajoules on top. We've got that conversion factor in the data table. And again, on the train, it's 1.1 megajoules per kilometer. So 1.1 goes on the top with megajoules, and it's per 1 kilometer. And this is going to be per person. And kilometers cancel, and now we have megajoules. So we're going to take 929 times 1.1, and our answer, of course, is going to be megajoules. And I'm going to let you do the math. You shouldn't have trouble with this part. So for the car, we're not going as far. It's a shorter distance. It's 618 kilometers. And for the car, it's 3.6 megajoules per kilometer. So this will be 3.6, and that'll be 1 kilometer on the bottom. And this is not for just the teacher, it's for everybody that's in the car, which is a little bit different. So the point here on that is, for a train, adding extra people to the train doesn't change the mass. It doesn't change much about the train. No, wait a minute. Adding extra people to the train, well, the megajoules per kilometer is listed as per passenger. But adding extra people to a car doesn't change the mass of a car very much, and it's listed as megajoules per vehicle instead. So they're rated in different ways. So if we had more people to spread out these megajoules, it would actually use less energy. So I'll let you go ahead and do the math on that one, and then we'll move on to the next question here. Okay, for the next question, it asks how much it would cost. It's $147 for the teacher to take the train. If she rented a car instead, how much would that cost? And the answer is $33 for the rental per day, plus the fuel cost. So really the question is how much is the fuel cost, and then we'll add that $33 in. And the fuel cost is going to be based on how far you drive. So the farther you drive, the more fuel you're going to spend, the more fuel you're going to have to buy. So for the car trip, it's going to be 618 kilometers. And we're trying to get to dollars. And we don't have dollars per kilometer for the car, but we do have kilometers per liter of gas. It's 18 kilometers for 1 liter of gas. Put kilometers down here so that it cancels, and liters goes on top. 18 kilometers goes with 1 liter. And now we can use our fuel price, which of course varies. And fuel efficiency varies by car too. So, these are just estimates. That's okay. $3.50 per liter. 1 liter, $3.50 goes here. And so we're going to take 618 times 350 divided by 18 to get our fuel cost. But be sure to add the rental cost in. Rental's just $33 a day plus whatever this fuel cost ends up being. So that's question 2. Question 3 is a little bit more realistic because this teacher is actually going to be not traveling alone, but she's traveling with her husband and child. So how much is she going to pay to get all 3 people between the 2 cities? Well, if she took the train, they would each cost $147 per person. So that cost is going to be tripled for the 3 people. If she took the car, however, oh, by the way, when you're writing out the problem for the train, you're saying it's $147 per person times 3 people. If this were an AP exam question, yes, you would have to write out 147 times 3 equals, and then write your answer down. I know that most of you know the setup in your head, and you wouldn't need to show the work for your brain to understand it. But in order to have the College Board agree that you understand the problem, you have to show them how you did the math. So you have to do 147 times 3 in writing on your paper. So then for the car, because we're adding extra people to the car, they don't charge extra for the rental, and it really doesn't cost much extra fuel. You do have more weight in the car with their baggage and everything too, and it will be slightly worse fuel economy, but it's not enough that we're going to try to differentiate between those two. So the car cost is going to be the same total cost for 3 people as it would be for 1 person, which is why it's usually a good idea to carpool if you can. Okay, so for question 4, we already figured out the per person number of megajoules for the train when we calculated what energy use we'd have for the teacher herself. But we also figured out how much energy the car was going to use, but that was for just the teacher or for all the people that she can fit in her car. It's going to be the same amount of energy. So we want to know the megajoules per person. So if you go back a couple of questions, you found the number of megajoules for the trip for your car, and now you need to divide that by the number of people in the car to find out how much energy it's going to cost, or how much energy you're going to use per person. So the per person energy use for the car, you're going to have to do math. The one for the train, we've already done. But I want you to compare the two. Think about that comparison. Question number 5, if you were the teacher, which mode would you choose and why? You can answer train or car, either one, but you have to support your claim with evidence and reasoning. And on this one, I'll tell you the actual result. The teacher has chosen to rent a car because for a lot of reasons. One is that we'll be able to get from Mont Saint-Michel to Les Aisies much faster. And so we'll be able to spend more time at our destinations and less time driving. It'll be actually lower energy cost and lower overall financial cost with a car as well, because we're carpooling with 3. If it was just 2 of us, it might be a different situation. We might make a different decision. But with 3 people, it's actually most economical for us to do the car. Some drawbacks to the car, though. One of you has to drive, so you don't get to stare out the window and look at the scenery and all that. You might get lost. You're driving in a foreign country, so that might be challenging. Certainly, probably will be challenging. So there's a lot of reasons why one person might choose one thing versus another. So either answer is fine. You pick the answer that you think is best. Also, we like the idea of not being stuck on a time schedule. Trains run on a schedule, and we want to be able to come and go as we please. So that'll be nice. And has nothing to do with math. Okay, let's move on to question number 6. This environmental science teacher recently got solar panels on her home. Here's what the solar panels are telling her today. I took this picture actually yesterday. So here we have, it says production today is 26.9 kWh and 3.08 kW is solar power now. So let's review again the difference between those two numbers. Kilowatt hours is the total amount of energy produced by those solar panels so far today. And 3.08 kilowatts, kilowatts is power. Remember, watts is power. Watts times hours is how much energy you've got. So kilowatts, that 3.08 kilowatts says that at the current moment, we're generating energy at a rate of 3.08 kilowatts. It's weird because rates normally have something per time, like miles per hour is a rate. We're used to rates that have per time in them. Watts already has that built in, which is weird and confusing. So the unit that has watts times hours, that's your energy. And the unit that has just watts, that's your power. So which unit refers to, wait a minute, the question is asking what amount of energy have the panels produced today? And so you're looking for the total production amount of energy. That's going to be your kilowatt hours. Don't forget you're going to round to the nearest whole number. So 26.9, we're going to call that 27. And make sure you have lowercase k, capital W, lowercase h. I know, weird. Weird energy stuff is weird. I don't know. Okay, question 7 then is what is the rate at which they're making energy? What's the power? The power is the 3.08. We'll round that to 3. And of course, lowercase k, capital W. And her Energy Star dishwasher uses about 240 kilowatt hours per year. Energy Star appliances, or any appliances, when you go to buy them, they'll tell you how much energy it uses per year, and it's almost always listed in kilowatt hours per year. So how many days of electricity production at this power rate would she need to convert her yearly dishwasher use, or to cover her yearly dishwasher use? So here's our power, and here's our kilowatt hours. So if we took the 240 kWh, let's write this one out, and we divided that by our power, let's call it 3, or you can use 3.08, it shouldn't matter. kW, kilowatts will cancel, and we'll have hours left. So once we do that math, 240 divided by 3, we're going to put our number here, and then our unit, and our unit, of course, is going to be hours. hours. How many hours would she need? Oh wait, that's hours, we need days. Uh-oh. I think I put the wrong answer on the key. I should probably fix that. No, that should be hours. Sorry. We'll change the question so that it says hours. So, yeah. Okay. Okay, we're looking at question 9 now, so let's take a look at that. Question 9 has that same teacher who bought an electric car to reduce her carbon footprint. Most recent month's energy use, and this is coming from my car's cell phone app. So it says that in the last 31 days, I charged 270 kilowatt hours. That's the amount of energy that was used to charge my car. And it estimates the total spent is $42. And that's pretty cheap, but that's charging 100% at home. My habits tend to be that I can drive. I don't drive enough that I need to charge at a supercharger. So if I did, that cost would actually be more, but that's okay. So daily charge rate varies depending on how far she drives each day, as shown in the blue bar graph. What is the average amount of energy per day needed to charge her car? And here's the total energy, 270 kilowatt hours, and that's in the last 31 days. So you're going to calculate how many kilowatt hours per day, and I'm going to let you go ahead and do that math. So you should be able to figure that one out on your own. So what you're going to put in the box is the rounded to the nearest whole number there, and then the unit is going to be whatever unit per day. Per day is already written in, so you don't have to put that in. Okay, on the next question, we are almost done here. Question 10 says, based on the power of the solar panels, how many hours of solar energy are needed to charge her car each day? And so you're going to take Okay, you're going to take the number of kilowatt hours per day that you just calculated, and then you're going to, so that's going to be kilowatt hours. You should have gotten around 9. Just do this one up here. So we've got 9 kilowatt hours, and we're going to divide that by 3 or 3.08 kilowatts, which is the power that the solar panels are producing. And so kilowatts cancels out kilowatts, and so we end up with hours. So that's the number of hours that I would need for solar each day to charge my car. So as long as we get more than that many hours of sunlight each day, then I should be able to have my car completely covered by my solar power. Okay, and then number 11. So here's a graph of last year's production, and it also shows January of this year. So on the graph, you're looking at blue lines and a green line. The green line is only in January, and it's to the right of the blue if you're having trouble seeing those colors. So describe and explain the trend that you see in the blue bar graph. The trend in just the blue bars shows that January, February, and December have the lowest electrical output from the solar panels, which should make sense to you because those are the months where we have the shortest number of daylight hours. Also, sometimes we have things like snow covering the solar panels, so that'll definitely block the electricity production. And also, the angle of the sunlight is lower. The sun is lower in the sky during that time because the Earth is, again, tilted away from the sun. And so that angle makes the electricity production less as well. And the highest months are March, April, May, June, July. Those are months where we get quite a bit of sunlight, many hours of sunlight. You might notice April is the highest, and that might surprise you because really June should be the highest. And the reason for this is that on the south side of my house, I have a couple of really big trees that provide a lot of shade, and they don't really start getting their full leaf coverage until like May. So April, they have no leaves at all. They provide very little shade, and so we're getting longer and longer daylight hours. But we really should see May, June, and July and August kind of up there with April, and that would happen if we cut down that tree, which is actually something we're planning on doing. And the last question is to compare that blue and green line for January. The blue line is taller than the green line. So make a claim to propose an explanation for the green bar being shorter than the blue bar. There are a few reasons you could say for this, and any of these would be acceptable. Last year, we might have had more sunny days than this year. I don't know if that's true or not. Last year, we might have had less snow than we had this year. That's a possibility. The solar panels are older and maybe need cleaned. Maybe they're covered in a layer of dust, so they're producing less. Also, we stopped collecting the data here on January 24th. However, the blue bar is the whole month of January, so it would show all the way through January 31st. So that green bar is definitely going to come up some. It's probably not going to come up to match last year's, though. It's probably going to be lower than last year's. Okay, hopefully that gives you an understanding of each of those kinds of questions. If you have any further questions or concerns about the energy math, send me a message and we'll figure out a time to get together during office hours or whenever. I don't have any other plans today. So, okay, have fun. Go play in the snow.